Okay, so we ended up last time with this big table, and it's hard to explain everything again, but I find it easier to do a table that person can read than you know, just set it all out in paragraphs, because then people don't necessarily pick up the structure. But we have our set structure, and then we have the restatement of the set structure in a vector space over Z2. And then we have the general vector space concept. And so each row tells us how to go through that. So
just a moment. Larry, could you mute? I think we might be getting some feedback there.
there you go.
Thanks.
So the talk today is to basically use this semi-algorithmic procedure to generalize logical entropy from set partitions to vector space partitions, and to generate the corresponding interpretation, the corresponding theorems, and everything over vector spaces. So this is the idea. The usual so-called quantum logic of Birkhoff and von Neumann basically did this for the logic of subsets. And so we go over from subsets to subspaces. So their logic is basically the logic of subspaces specialized to Hilbert space. And you get some additional structure when you specialize Hilbert space, orthonormalization, complements, and so forth. So I'm doing the same thing, but I'm starting with partition logic and logical information theory defined on partitions, set partitions, generalizing that to vector spaces in general. And then you can specialize the Hilbert spaces, although I haven't really worked out many special features because the main idea is to get it all working in vector spaces and not just sets. So we start with logical entropy on sets. You start with partitions, but it's good to think of all partitions as being generated as the inverse image of some numerical attribute. And here we can take the numerical attribute, taking values in a field K, so that could be the reals typically. And then we saw last time how the corresponding vector space notion is a direct sum decomposition, and direct sum decompositions can be seen as defined by these diagonalizable linear operators. But here we're going the other way around. We start with this function little f, and we define the linear operator on the space. And this U here, we're assuming is a basis set for the space. So that's the trick, is you apply a set concept to a basis set for the space, and you see what it generates. And in this case, we saw it generate two things: a linear functional and a diagonalizable linear operator. And it's the latter, the linear operator, that we really want, because we're really want to do quantum theory here eventually. So given this function small f here into the underlying field, here is your definition of the linear operator. Applied to any basis set U, it's f of u times u. And so you define the operator in a basis set, and then you generalize it linearly to the whole space. So that's the step one here. And then for sets, we have distinction. Distinction is ordered pair of elements in different blocks of the partition. But the blocks of the partition we're now thinking of as being generated by inverse image of this function. So that means just different values for f, because each block in the partition is one value of f. So, so that's our notion of a DIT. ordered pair of elements of U with different values. So a qubit, not a qubit, but a qubit is an ordered pair. And I'm now going to write the ordered pair as a basis set for the tensor product, because we saw back here that the direct product of sets, which is the ordered pairs, you can do the same in vector space over Z2, but in general, the corresponding notion of a direct product is a tensor product, not a product of spaces, but a tensor product of spaces. And the ordered pairs go over into ordered pairs of singletons in the power set here, or just if we think of U as just basis vectors, we don't have the singleton thing. We could put in kets here if you want the ket symbol. So the basis set for the tensor product is just the ordered pairs of these two elements. So, so what is the corresponding notion of a qubit in a vector space? Would be obviously the linear operator which on these basis sets would give you distinct eigenvalues, because these f's here are obviously the eigenvalues of the function that you just defined, the operator. So distinct values or distinct blocks in the partition go to distinct values of small f, and that means distinct eigenvalues for big F. So that's what a qubit is. A qubit is a basis element in the tensor product. So the inverse image here is just the dit set, the set of all distinctions, all the ordered pairs of elements in different blocks of F inverse. So over here we have, remember, sets define spaces. So the analogy of the dit set generalizes to the qubit space. That's where the square brackets are here. Subspace of the tensor product generated by all the qubits of F. So F is defined on V, but you think of as if you're making two measurements of F, as you get two eigenvalues, and so all these ordered pairs, which correspond to different eigenvalues, generate a space in the tensor product. So that's a qubit space. So qubit space is the vector space version of a dit set. And so that gives you how the machinery carries over, and much, as I say, much of the machinery can be carried over even before you bring in probabilities. So this is interesting on two accounts. One account, Kolmogorov criticized Shannon, saying that Shannon defines his entropy using probabilities. And you remember that Shannon entropy is not a measure on the set. If you had an underlined set, you'd have some notion perhaps of information from that set, but Shannon never did that. Shannon started off directly with probabilities, and Kolmogorov criticized that, saying that information should be defined by some, finite combinatorial object prior to bringing in probabilities. And of course, Kolmogorov had his own idea in mind, which eventually developed in complexity, Kolmogorov complexity theory. But from my point of view, I love the quote from Kolmogorov, because here it is. Here's the dit set in the set case. That gives you what information is distinctions, and these are the set of all distinctions. And so when you do that in the vector space sense, the qubit space is the corresponding notion. So no probabilities here. And so the next table, this whole table brings out all these analogies without any probabilities. So now let's go over some of these rows here. So suppose you had two functions on U, F and G. Now, as you know, in quantum theory, you have this notion of commuting operators or not commuting operators. So the set version of commuting operators simply means defined on the same set. And when you carry it over to vector spaces, that means operators commute, but that means that there is a common basis set of eigenvectors. So a basis set of simultaneous eigenvectors of f and g. So, so defined on the same set, and here a common basis set, as it were, for the two operators. So they're commuting operators and they're self-adjoint because we're talking about observables here. So here's your set on this side. Here's your basis of simultaneous eigenvectors here. Here's your values of f. So these would be all the eigenvalues of the operator f. And the gammas here are the values of g. So those are the eigenvalues of capital G, the operator. It's defined. Inverse image is the partition, and the corresponding thing for the f operator is its direct sum decomposition of eigenspaces. And similarly for G, you have a direct sum decomposition of eigenspaces. And you remember also that, so if you take these two, if you think of the join of two partitions, it's the partition of all the intersections, non-empty intersections of the blocks. So the blocks of given partition cannot intersect with each other, but given two partitions on the same set, like these two, the blocks can intersect. And so the same thing here. You've got two direct sum decompositions on the same space V. So you can do the same construction, is take all the, because the intersection of two spaces is a space. And so you take the set of subspaces that are the non-empty or non-zero intersections of these eigenspaces. So that gives you a whole set of subspaces of V, your vector space, but do they span the whole space? Because we know that the direct sum decomposition of f and g, each one spans a space, but there's no guarantee that when you take those intersections, that they will still span the whole space. And the theorem here is they do if and only if they commute. So commuting operators means that their direct sum decompositions joined span the whole space. So you get the notion of join coming out of partition logic, directly applying here and reproducing the notion of commuting operators. And in this case, they do commute by the way we define them. We define them on the same set. So we know we already have a simultaneous, a basis set of simultaneous eigenvectors. And if you have that, then of course, the operators are going to commute. That basically says that commutation boils down to commutation over the base field, and all the base fields are commutative. So then we go down a little further, we get to the dits. We've got the dits of f, we got the dits of g, now we got the q dits of f here. We got the q dits of g here, and I'm saying here that the f values are different, but that, remember the f values are just the eigenvalues in when you define the function. So here you got the dit set, here you got the q dit space, subspace generated by the q dits, and then you can just, when you do the compound notions of logical entropy, you have the union of the two dit sets, which in this special case is in fact the dit set of the join. Then you have the difference, which is not a dit set of a partition, and you have the intersection, which is not a dit set of a partition, but by applying the probabilities when they finally come in, there's no probabilities here yet, then you get the logical entropy of the join, you get the conditional logical entropy, the logical entropy of pi when you take away the information in sigma, and vice versa, as well as the logical information contained in both. So, so this intersection, for example, is not a dit set, but if you take its interior, which would be a smaller set, that is the interior is the biggest dit set contained in both. That's the dit set of the meat, the meat of the two partitions. And remember, the meat and the join of partitions was known in the 19th century, known to Dedekind and to Schroeder. So here we have now just the same construction. Obviously, once you get the system going, it just generates the same subspaces for the join, subspaces for the difference, subspaces for the intersection. And so we have now these notions of quantum information carried in these subspaces, which are the subspaces of these generated by these points with different eigenvalues of f, different eigenvalues of g, and we know probabilities yet. But what we're going to do is now, once you bring in a state, so there's no state here. We're just talking about operators. There's no state. When you bring in the state, that's what defines the probabilities in quantum theory. And so the next table we're going to get is when we bring in a state, and then we're talking about measurement, because then we have operators, we have measurement of a state by those observables. So let's move on to the next one here. So in the set case, we have our dit sets, which are typically the inverse image of some numerical attribute. And then we apply, we're just, in the set case, we just assume we're given a point probability of the points in U. And so we don't have the notion of bringing in a state here. We're just bringing in the probabilities. So the elements of U could be equal probable, or they could have some point probabilities. But any point probability distribution on U generates a product distribution on the product of U cross U. And that's where dit sets live. Dit sets live in U cross U. So this is a probability distribution on the dit set, and that's your definition of logical entropy. So it is a measure in the sense of measure theory. It's in fact a probability measure, and so forth. So we now start to move to the quantum case. Probabilities enter in when we have a state, and once you have a state, then you have a density matrix, and the density matrix then generates, just as you have P cross P here, you have the density matrix cross the density matrix, which is a matrix on this tensor product space. Now, the probability of getting a certain eigenvalue in the measurement is the trace of the projection of the qdit space times the density matrix. So this is the way you now extract a probability using a measurement. So I have this, the next formula here. Where are we here? Yeah. So let's approach measurement by starting off with a pure state. So you remember, a pure state doesn't mean it's an eigenstate. It means it's a superposition of eigenstates, whereas a mixture is just the classical notion of, you know, certain probability you got this state, another probability you got that state. So we're starting off with a pure state to do a measurement. And the corresponding thing for the set case, the pure state is just the blob, because the pure state here means you haven't made any distinctions. Everything is coherently superposed in the pure state, the superposition of the eigenstates there. So the corresponding classical notion is just the blob, the indiscrete partition. So here's your set, and now we have, if I talk here about orthonormal, then I'm assuming here the inner product space, and which could be the reals or the complex. So we have simultaneous eigenvectors for our two operators. We have a probability distribution here, which we assume is given. Here we brought in the state psi, and so we have these two tensor product of these two matrices, which is a matrix on the tensor product here. And you remember so this would be n squared times n squared. And so on the set case, logical entropy, because it's the blob makes no distinction. So its logical entropy is 0. And here, all pure states are equal to their a square of their density matrix. That's the definition of a pure state. So, and the density matrix by definition has to have trace 1. So you got 1 minus 1 for a pure state, and that gives you 0. So we have the analogy carrying through there. So now we want to bring in here a partition, and over here we're going to bring in an operator. So here we bring in partition pi, which could be our F inverse, and we have the logical entropy defined. So over here, the corresponding definition is to take the projection operator down to the qubit space of F. So this is the subspace generated by all the ordered pairs of basis sets that have different eigenvalues there. And then you take that times we're operating the tensor product. So we have this matrix here. So you have this projection operator times this matrix, and that gives you the trace, gives you a logical entropy. So the question is, well, what is that logical entropy? And before we get to that, just notice you just substitute in the union of the qubit spaces, the difference qubit spaces and all that, and everything just goes through. And since this is the conditional, this is the mutual or the common intersection as a common information, then you immediately get that this is the, just like in the classical case, is the information in F that's not in G plus the information that's in both F and G is the information that's in F. So and the same over here, you have the distinctions that are in pi but not in sigma, plus the distinctions that are in both. So that's your usual, you get that from the Venn diagram. But the interpretation is the interesting thing here. So here, if you make 2 draws from the underlying set, which has probability distribution on it, then what's the probability that you got different F values? Remember, that's your logical entropy of pi here is the 2 draw probability that you get different F values. So here, rather than 2 draws, you got 2 measurements. So this interpretation of this thing we defined up here turns out to be, if you make 2 measurements on the same pure state psi, then the probability you'll get different F values. If you're doing F measurements, it's this. So the 2 draw interpretation carries over. And then we could also specify another way to specify this same thing here is to start back over here with sets. You can find certainly a density matrix for a partition, and you can even, here is the Luder's mixture operation. You remember you start with the beginning density matrix and you pre and post multiply by all the projection operators down to the, in this case, sets, and then you add them up. That gives you the density matrix for pi. And the same thing over here. You're starting with a pure thing. You have your eigenspaces here, which correspond to your blocks here. Take pre and post multiply. So this is your Luder's mixture operation, and you get rho hat. So rho hat is the post measurement. You're doing a projective measurement by the F, and the VIs are the eigenspaces of F. So the Luder's mixture operation describes the change in the density matrix from your pre-measurement density matrix, just rho of psi, to rho hat of psi. And then you do the same thing like remember when we do logical entry is 1 minus the sum of the probability squared. So the corresponding thing here is the 1 minus the trace of the density matrix squared. So you do that here, you take 1 minus the trace of the rho hat squared, and that gives you this post-measurement logical entropy. So it's the, as it were, the quantum distinction is generated by the measurement. Then there's another way to characterize it. we got a process here, the Luder mixture operation, going from row to row hat by doing this pre and post multiplication. And so you look at all the entries in row of psi that get zeroed. So remember, we're talking about off-diagonal entries. So the off-diagonal entries indicate that those two states are cohered together. But when you measure, they may get decohered. That's what measurement's about, is decohering states that were previously cohered together. So all the off-diagonal elements that get zeroed are precisely the distinctions, the decoherences created by the measurement. And so you just take their absolute squares and you add them up and you get the same logical entropy here. So you get all these different ways of defining the same logical entropy of the operator given on a state, which is basically describing what happens when you do an F measurement on a pure state, psi. And all this generalizes if you start off with a mixed state, and then you just get a more mixed state when you do this sort of measurement, projective measurement. So it's always helpful to actually work through some examples. I think I got one example later on, but the interesting thing to imagine in your head, imagine this density matrix with all these off-diagonal elements indicating the eigenstates that are cohered together in the pure superposition. So when you do a measurement, you're knocking them out. Some of them, because you're decohering those two eigenstates, so they no longer are in the superposition. And so how do you knock out an off-diagonal element in a matrix? Well, you're pre and post multiplying by a projection operator. Remember, projection operators are just a bunch of ones in the diagonal, otherwise they're zeros. So each time you do this pre and post multiplication by a projection operator, it will keep something in there if it's already corresponds to the same VI. So you knock a bunch of them out and then you add them all back together. So the ones that don't get added back together were the ones that were in different VI and VJ, in different eigenspaces. So they got decohered. And then you add up all those ones that got zeroed, and that gives you the quantum measurement here of the distinctions that were made, quantum distinctions that were made by the measurement. Let me drink some of my chicken soup here. All right. So that's the main idea here. The usual notion of von Neumann entropy in logical information theory doesn't even, first of all, has no interpretation in terms of it's the probability of getting two different eigenvalues in the measurement. No such thing. It doesn't even have any compound notions because they couldn't figure out how to generalize the Shannon case, which just started off with probabilities and it didn't start off with a set, because I generalized the set here to the subspace, which is how sets generalize to subspaces, and then laid on the probabilities in the way they're usually brought together, trace of a projection operator times the matrix, and then gives you that logical entropy. So the von Neumann entropy doesn't even have any of these compound notions, not to mention interpretation of probability of different eigenvalues. But that's the notion that's embedded in the field. And so I suspect maybe in a decade or two, these new notions may soak in enough, but it's hard to change these things once they get, you get a whole field, as it were, using the von Neumann entropy only. And it's the von Neumann entropy. So it has a lot of pizzazz attached to it. So here I just go through a simple example. This is sort of a standard example. We have a 1/2 spin particle, and we're measuring on the z-axis. So this our set u is the up and down spin on the z-axis, and the eigenvalues are +1 and -1. So up is 1, down is -1. So that then defines an operator on the complex number squared. And here is your definition of the capital F, the operator on the basis set, and then it generalizes to everything else in the underlying space C2, because these are the basis sets. And when you express the operator in its own basis set, then of course it's diagonal, it's diagonalizable, and the diagonal entries are the eigenvalues. So all that is familiar. So now we take an arbitrary state, which is an arbitrary superposition of up and down, and so this is your column vector representing the state, and I'm not specifying what the alphas are. I mean, assume the thing is normalized. So your density matrix, remember you multiply on the left this thing by its conjugate transpose. So it's a row vector for the two conjugates, and you multiply it out, and then you get this thing here where the alpha up times alpha up conjugate gives you the probability, and similarly for down. And here you get the cross things, the alpha up and the alpha down conjugate, and vice versa over here. So that's your density matrix. So let's now form the tensor product of this density matrix. So here we go. So you remember when you do the tensor product, you have the matrix on the left, you have these scalar entries, and then you put in the entire matrix on the right, which is again this row. So you have this probability of up times the whole matrix, here this cross term, off diagonal term times the whole matrix, and then you spell it out. So this 2 by 2 here is just this term here spelled out, and this 2 by 2 here is this term spelled out, and so forth. So that's the row times row. So that's a matrix that operates on the tensor product V tensor V, where V is here just C2. Now, what are the qubits? Well, the qubits of F, which F we just defined, are these two basis sets, which have different eigenvalues. So it's up crossed with down and down crossed with up. So those are the two qubits. And so you want to then, so they generate a subspace, the qubit space of all the things you generate in the tensor product from these qubits here. And so you have that subspace, and then you want to do the projection down to that subspace. You remember our thing here, we had the projection operator down here to the qubit space. And we want to multiply that times this tensor product and take the trace. Okay, so here we go. Here's our tensor product. Remember I said the projection operators are just diagonal matrices with ones and zeros on the diagonal to say where you're going down to. And I'm implicitly using, I've got to identify the rows here, but it's sort of obvious what the rows and columns are. So the first row and column is up times up, and then up times down, and then down times up and down times down are just the labels of the rows and columns. So these two entries correspond to these two entries, where you have up times down and down times up. Okay, so that's your projection operator. So let's now multiply this projection operator times this tensor product. So here we go. Here's our projection operator. Here's our tensor product. We multiply it all out here, and we then take the trace. We're going to take the trace in the end. So we take the trace. It's just 2 times the product of these probabilities. Okay. So what's the interpretation? So the interpretation is that this is, if you did 2 probability in 2 different eigenvalues in 2 independent measurements of that state sigma by the observable F. So what's the probability that you get up on the first and down on the second? Well, it's probability up times probability down, but we're dealing with ordered pairs here. So what's the probability you got down on the first and up on the second? It's the same product of probabilities. So the sum of the probabilities of getting different spins in 2 measurements is 2 times that. And that's exactly what we got by going through all this calculation here. Okay, and I'm not sure I did all this in the first set of slides I sent you, but maybe the second set I did this calculation. So it's totally intuitive, the result. You're doing 2 measurements, and the probability of getting up is P up and P down. So the probability you get up and down on the 2 measurements is the product of 2 probabilities, and then you do it the other way around. You get P down on the first measurement and P up on the second measurement. And so the probability you get different ones in either order, just 2 times it. And that's exactly what we get here. So it's all obvious. But we said, well, there's another way to do it. Let's do the Luder's operation. You remember we had all sorts of different ways to go here. We had this way of going. Where are we here? Here, this H logical entry was, I just computed this. Okay, so let's now go down and compute the Luder's mixture operation, and then to get rho hat, and then take the trace of rho hat squared and subtract it from 1. So we'll do a different operation, okay? And then we'll do the third way. We'll sum up the off-diagonal terms that got squared. We'll get the same result every time, okay? So let's just verify that. So here we go. Here's the Luder mixture operation. So we're starting off with rho. Here is our original rho right here, pure state density matrix. And so we're pre-multiplying and post-multiplying by the projection operator down to the up space. And now we're working in C2, not the tensor product. So we got 2 by 2 matrices. So here's the, so they're obvious labeling the rows and columns up and down. So here's the projection operator to the up eigenspace, pre-multiplied, post-multiplied, or maybe we should call this pre and this post. And here's the other way around. Now we're doing the downs. So the 1 is down here for the down. And what do we get? Just add them up. And so we get the diagonal matrix of rho hat. So let's now square rho hat and take its trace and compute the logical entropy that way. So we go over here. So when you square rho hat, then I don't know if I put in the actual calculation here, but it's a diagonal matrix. So you don't have to do a lot of calculations to know what happens when you square a diagonal matrix. It just squares the diagonal elements, right? So here we have it, and you take its trace. So the trace is just the sum of these 2 things squared. Here it is. And you want to subtract that from 1. All right, well, what's that subtracted from 1? Well, you remember that the sum of the 2 probabilities is 1. So when you take P up plus P down, you square it, you get these two squares and this cross term, and they add to 1. So when you subtract the two squares, you get the cross term. And that's the cross term, exactly what we got before. All right. So that's the second way to calculate logical entropy. And these are all theorems. These are not just things that work for this example. So let's go back here to the third way. Here's the third way. Take the sum of the absolute squares of the entries that got zeroed and going from the original matrix to the post-measurement matrix, the row hat. Okay. So here's our original matrix, and here's our post-measurement matrix. So the terms that got zeroed are both off diagonal elements. So what is their absolute squares? Well, you know the absolute square, so you take this one times this, which is its conjugate, transpose, and that gives you P up times P down. And then you take this one, which also got zeroed, times its conjugate at its value absolute square, and that's P up plus P down. So the sum is 2 times P up plus P down, which is right here. So, and here's that thing you have to use, that the two sum is equal to 1, you multiply it out, so this thing is equal to 1 minus the sum of the squares. So that's it. That's the 3 ways to calculate the logical entropy of a projective measurement of a pure state. All this goes over to mixed states and so forth. But the 3 ways to get it, none of the structure exists for the von Neumann entropy. It has no interpretation as the probability of getting 2 different eigenvalues on 2 different measurements of the same state, and there's no connection. I mean, obviously, for the von Neumann entry, you're gonna have the same. Going back here to the table, this is the Luder mixture operation. See, this doesn't involve logical entropy at all. It's the same if you have, you know, using von Neumann entropy or logical entropy or whatever. It's not an entropy calculation, but when you can get the logical entropy by just taking the sum of these absolute squares of what happens when you do the Luder's mixture operation, and that gives you logical entropy. Nothing like that holds for von Neumann entropy. Von Neumann entropy increases with projective measurement, but you can't calculate its new value from just the change in the density matrix, which is given to you by the Luder's mixture operation. So that's 22 slides out of 22. So that's it. That's the introduction. There's a lot more, of course, in the book that I sent you, and there's another. As I mentioned, there's a special issue of this new journal coming out on logical entropy, and so I've got a long introductory paper in that, and I go over a lot of these examples in that paper as well. So that's it. I will take another drink of my soup.
Wow.
This is fantastic.
You can stop recording if you want.